Hi everyone, before we start our presentation, let me introduce first our team members' name. So we have Putri Alisha Amira, and my name is Afrika Nawara, and we have Sharifah Kristina and Nurfatina Sohab. We are from Group 5 AS1243B. So now we will present to all of you about the topic that we choose, which is detection of toxic metals in common spice.
Okay, introduction to volumetric analysis. What is a volumetric analysis? Volumetric analysis is a method in chemistry used to find out how much of a substance is present by measuring the volume of a solution needed to react completely with it. It is widely used because it is simple, accurate and reliable for laboratory experiment. So why it is used for detecting toxic metal in spice? In spice, heavy metal like lead, cadmium or nickel can be present due to soil, water or contamination or processing methods. Volumetric analysis allows researchers to measure the exact amount of this metal in spice sample, helping to understand the level of contamination. Importance for food safety and human health. The first of all is regular consumption of spice contaminated with toxic metals may accumulate in the body and cause health problems over time. Using volumetric analysis ensure that the metal levels are checked, quantified and compared to safety limits so that the spice consumed are safe for human consumption. Okay, why do we test spices? As we know, spices are organic food additives that have been used to improve the sensory quality of foods for thousands of years and have been an integral part of worldwide culinary traditions, providing flavor, aroma, and medicinal properties and playing important historical roles in civilization, exploration, and commerce. Okay, the second one it is to monitor the presence of heavy metal in food, spice, and herbs. Spice and herbs contain varying levels of heavy metals depending on their type and origin, which is makes continuous safety and monitoring necessary. The third one is spices and medicinal plants contain heavy metals that are essential to living cells. That means to understanding the content of trace metals in foods is critical because of their essential or hazardous effect on human health. So the last one is to assess potential health risk to human. Heavy metal contamination in spice and herbs pose significant health risks, such as lead, arsenic, and cadmium that absorb this from contaminated soil or water, posing some health risks to consumers, especially with high spice intake, making testing crucial for food safety, regulatory compliance, and protecting public health, not certified laboratories.
Complexometric titration is a volumetric analytical method used to detect and determine the concentration of toxic metals such as lead, cadmium, and copper in a sample. This method is widely used because it provides quantitative results, meaning it can measure the exact amount of metal present, not just its presence. In this method, EDTA is used as a complexing agent due to its strong ability to bind metal ions. When EDTA is added to the sample solution, it reacts with the metal ion to form a stable metal. By measuring the volume of EDTA used during the titration, the concentration of toxic metal in the sample can be accurately determined. I will explain how complexometric titration works. EDTA will react with the metal ion present in the sample and form a very stable complex in a 1:1 ratio. For example, one EDTA molecule binds one metal ion. During the titration process, EDTA will bind the metal ion in stage until all free metal ion in the solution have been completely bound. Indicators such as areochrome black T are used to facilitate observation of the endpoint of the titration. Initially, the solution shows a certain color because the indicator is still bound to the metal ion. When all the metal ion have been bound by EDTA, the indicator will be released and the color of the solution will change. The color change marks at the point or end point of the titration. Acid digestion for metal extraction. Acid digestion is a very important initial process in metal analysis because most food samples such as spice are in solid form and have a complex organic structures. This process aims to destroy the solid sample using strong acids such as nitric acid or hydrochloric acid. This strong acid will decompose organic materials in a spice, such as plant fibers and natural pigments, which can prevent a metal detection. Through this process, toxic metals contained in the sample will be completely released into a solution, thus allowing metal analysis to be performed more accurately using subsequent method. So, this is how acid digestion works. Spices have a complex organic structure because they contain plant fibers, essential oils, and natural pigments. This structure makes the toxic metal found in spice difficult to detect if the analysis is done directly. When a strong acid is added, the acid will decompose and break down the organic structure, thus releasing toxic metals such as lead and cadmium into a homogeneous solution that is easy to analyze. So why acid digestion is very important? It is because without the acid digestion process, toxic metal present in spice samples are still trapped in organic structure, such as plant fiber and natural pigments. This situation causes the metal to not be completely removed and thus makes accurate detection difficult. Therefore, acid digestion is very important because it helps destroy the structure of the sample and release toxic metal into solution. In this way, metal analysis can be performed more accurately, effectively, and provide more reliable results.
My name is Afika. So now I will proceed to explain the acid digestion procedure. First, we need to weigh about 1 gram of the powdered sample into a clean beaker. Next, we need to add concentrated nitric acid, which is HNO3. Then add the hydrogen peroxide, which is H2O2. Heat the mixer on a hot plate or in the microwave digestion system at around 120 Celsius until the solution becomes clear. Allow the hot solution to cool to room temperature. Once cooled, we need to transfer the digested solution into a volumetric flask and rinse the beaker with deionized water. Add all the rinse into the flask. Then dilute the solution with the deionized water up to the required volume and mix well. Don't forget to prepare a blank digest by repeating the same steps but without adding any sample. Last but not least, we need to label to both of the volumetric flasks with the word sample digest for the solution that have powdered sample, and the word blank is to the volumetric flask that have the solution without adding any sample. Then store them properly until analysis.
This is the example of results that I get from the Google. So this is a complex geometric titration result. First, this table shows the titration result for the sample. 3 trials were conducted to improve accuracy and reliability. For each trial, the initial and final volume of EDTA were recorded, and the volume of EDTA used was calculated. From the 3 trials, the volumes of EDTA used were 10.3 ml, 10.1 ml, and 10.2 ml. The average volume of EDTA consumed by the sample during the experiment was calculated and found to be 10.2 ml. For the blank experiment was carried out using the same procedure but without adding any sample. This step is important to correct any volume contribution from regions or impurities. For the blank, the volume of EDTA used in the 3 trials, which is 0.4 ml, 0.3 ml, and 0.5 ml. The average volume of EDTA consumed for the blank was 0.4 ml. So for the step-by-step calculation, first is corrected value of EDTA. So the formula is average of sample volume will be minus with average of blank volume. So the corrected value that we get is 10.2 minus 0.4, and the final answer is 9.8 ml. The second one is moles of EDTA, and the formula is corrected value will be multiplied with molarity of EDTA. If molarity of EDTA is 0.01 m, so the moles EDTA that we get is 0.0098
liter will be multiplied with 0.01 mole per liter. So the final answer that we get is 9.8 times 10 to the power of minus 5 mole. In complex geometric titration, the molar ratio between EDTA and the metal ion is 1:1. So it means the moles of metal will be same with moles of EDTA. For the concentration formula, moles will be divided with volume sample, which is in liter. So the sample volume is 10 ml, and when we change to the liter, we get 0.01 liter. So the concentration that we get is 9.8 times 10 to the power of minus 5 mole per liter, and we divided with 0.01 liter, and the final answer is 0.0098 m. So what I can conclude here, based on the complex geometric titration results and calculations, the concentration of metal ions in the sample was determined to be 0.0098 m.
In conclusion, this study shows that analyzing spice for the presence of toxic metal is very important to ensure the safety of the food we consume. Spice can be contaminated with heavy metals such as lead and cadmium due to pollution from soil, water, air, or during processing and manufacturing. In this investigation, volumetric analysis using complex geometric titration with ETA was applied to detect and determine the amount of toxic metals in spice samples. Prior to the titration process, acid dissection was carried out to break down the organic structure of the spice and release the metals into the solution, allowing accurate and reliable analysis. Overall, the method used in this study play an important role in ensuring the quality and safety of spice and in protecting public health. Therefore, regular testing of toxic metals in spice is necessary to minimize potential health risks to consumers.